Okay, welcome to Module 38. What is machine learning? So we're going to talk about what do we actually mean by a machine learning model in this course, how machine learning, ML is short for machine learning, tasks like classification or regression fit into a broader data science pipeline that you've already seen. We have talked a little bit about training and validation and testing before, so we're going to talk about what can go wrong if we ignore them. And we're going to talk a little bit about how relatively simple machine learning workflows look in Python, at least at this level. At the end of this module, you ought to be able to explain what machine learning is, at least in a very high-level manner, and differentiate it from popular conceptions of what machine learning is. It's not just writing rules, for example. You'll be able to classify, so to speak, among common machine learning tasks like regression and classification and maybe some other types. You ought to be able to describe and justify, why we have training, validation, and test splits for supervised learning. And you'll even be able to implement the beginnings of a simple machine learning workflow in Python that splits the data, trains a model, and evaluates it on some held out data. We'll also talk a little bit about diagnosing a few evaluation mistakes. I want to mention for the moment, machine learning is sort of the primary area of focus for artificial intelligence research, and to some extent, everything we've been learning in this class with regards to data science generally, has its own purpose, and there's a lot of data science you can do that has nothing to do with machine learning. But we've been kind of pointing in the direction of, well, we want to have a representation of some phenomenon or phenomena that are in the data. And, so we need to pre-process, we need to, handle sampling appropriately, we need to get our, quantitative metrics and statistics all sorted out and understand how to run experiments. And we can do all of that stuff without machine learning technically, but it was all pointing towards the idea that we want a model or representation of whatever it is we care about, whether it's patients in a hospital or customers in our store or students in our university. And how do we produce models or representations of these concepts? Well, in the old days, we'd have people just write up, massive flow charts or flow, diagrams that would indicate or represent also what this information was and how to behave if you saw certain inputs to a program. But, that doesn't scale well. There's all kinds of other challenges we won't have time to talk about today. But I just can't emphasize the extent to which machine learning, learning models automatically, I guess, automatically from data is so powerful and so important, and also because of its importance and because of its power, we need to understand ways in which it can go wrong and how to mitigate against it. Okay, so this, I think I might have said this a few times already, but this is also a very important series of concepts. This is going to be an important module. I have pilfered a little bit from my third year class on machine learning to get some slides for this course, just to avoid duplication. It's not going to be too deep though, right? So the slides come from a very early part of the third year class, and we're not going to go very deep on any new concepts in this module. As I was kind of complaining about, in the old days, so before machine learning really took off, this is more than a decade ago now, but we're still going through the transition from classic traditional programming to machine learning. You might have a challenge in a bank to write a program to indicate whether or not you should flag an application for a loan as risky or not. And we talked a lot in this class about having lots of observations, like you measure balance, you measure how many days they're overdue on a previous loan, you have some statistics or some measurements for these. And in the old days, you might just literally write out a if statement like the one that we have here. If certain conditions are both met, then you flag the application as risky and go on with your life. Now this can be expensive to write. It took me a second just to read this off, but you have to hire an expert in both programming and in loans to encode information about some knowledge about how banking works and how loans work and what's risky and what's not. It's very expensive, and it might work for a time on a small example of essentially validation data, which we'll get to momentarily, but it's going to be brittle. It's going to not going to deploy robustly. It's going to fail. Now, what we've been pointing to a lot of this time is towards machine learning, in which we have a ton of examples stored in something like a data frame of inputs and outputs. The inputs might be something like, GPA, previous quizzes, activity logs, and then you have outputs that you want to try to predict. Will this student complete their quiz next week? Yes or no? Back to the previous example, given all this information we have about a customer in a bank, should this be flagged as risky or not? A learning algorithm, in some sense, searches, I should put searches in quotes, for rules that work well on the examples that it has at its disposal. And that search, again speaking loosely, is a process called training, and the examples are provided to it in a cleaned and careful manner. Once the model has been trained, it should be good at making predictions on new cases it's never seen before. Therefore, we stop updating the model and we say make some predictions about new cases and then we evaluate it to see how well it does on generalization. How well does it do on data it's never seen before? I say I should put searches in quotes just because searching is a set of tasks that involve different kind of approaches and different algorithms than machine learning. Like they're related but different. Often they overlap, but not always. I just wanted to highlight that it's a little bit different. So we'll be more specific in a moment. I guess the shortcut definition is that machine learning is about automatically learning patterns from data so that you can make predictions or make decisions about new cases without hand coding the rules. Now, how it does it can be obvious to us when we look into the model or the representation. Sometimes it can be less obvious, and there's lots of challenges, which we'll talk about a few of them in this next sequence of modules. So we've seen how to frame a question, like what decisions are we supporting. We've seen how to clean the data and to prepare it. We've seen a little bit about how to explore the data and visualize it. That is important, even before you do machine learning, to understand if there's any hidden relationships or any obvious challenges in terms of the distributions of data, any patterns that might be emerging beforehand that would maybe bias the machine learning process. All that's important on its own and for machine learning. There's a little bit of causal thinking. So machine learning models, there's a variety of them. There's a lot of them, and some of them are trained more to find correlations in data. In fact, I just put together a module on some relatively deep neural networks to learn about language and about vision, like images, and those are often based on correlation statistics. So, this word often appears together with these other words, therefore there's some relationship. But does one word cause another? Well, even some of the deepest models don't necessarily learn that right off the bat. So you have to be careful. So we know that already, but now we're going to add an idea called supervised machine learning, where we learn a mapping from input features or input data to a target. So given input, what should the target be? We'll talk a little bit about evaluation, and we'll also just highlight again that machine learning isn't the whole story. I mean, I know in some sense we've been aiming for this, and this is sort of the centerpiece for a lot of data science work. Sometimes it's primarily focused. Sometimes it's merely an important part of the overall process. Sometimes it's not even included, but it's only one tool amongst a variety of other tools that we have at our disposal. I can't emphasize that enough. So we want to maybe just separate out kind of high level two kinds of machine learning task types: supervised learning and unsupervised learning. In supervised learning, we do have a target, like I mentioned a moment ago, and we have input features, and we're trying to predict the target from the input. And there's two sub-ways of doing supervised learning also. There's more, but for now, we'll just talk about these. Classification, the target is a discrete category. We've called them nominal categories. They're labels, like at risk or not at risk. Will pass, won't pass. This is a picture of a cat or a dog or a plane or a boat or whatever. Those are all categories. And the kinds of tasks you might have are things like fraud detection. Is it fraud or not? Is it spam or not? Is this disease X or Y or Z or omega or whatever? So those are taking a variety of kinds of inputs and then trying to label that data point. Regression is very similar in many fundamental ways, but it's about predicting a numerical value. So you might have information about how many people are at a table, and is it lunch or dinner, what time of day it is, how much did they pay for their meal, and then try to predict on a scale what the percentage of the tip will be. Or give it information about a region and qualities of a house, what the house price is going to be. Or given information about a waiting room, what the wait time will be. Percentages in percentage, house prices in dollars, wait time might be in minutes or hours. And each of these are measured on a continuum. So again, classification and regression, they have a variety of inputs, and those inputs are meant to predict an output. We know the output that we should be predicting. We have that available to us when we're training our model, so we can learn the correspondence between these things. And a lot of the same problems exist between both. So we're going to dig in a little bit to regression, but even simple regression will suffer from the kinds of challenges that the massive deep neural networks do at the highest orders of magnitude. And the only difference between classification and regression here is whether we're predicting continuously valued numbers in the case of regression versus nominal categories in the case of classification. All of supervised learning, set it aside for a moment, and then briefly talk about unsupervised learning. There's no explicit labels. We only have features X, and that's it. And we have to still learn like a model that represents these features X. So clustering customers into engagement profiles, like groupings. If all these customers, all these receipts, you want to group them together. So you say, well, these customers, I've learned automatically using machine learning that they're all similar in some fundamental ways. So if a new customer comes in and they're very similar to this particular cluster that I found, we can expect that new customer to behave in ways that are similar to these old customers I've previously collected in my training data. So the key difference here between unsupervised and supervised learning is that unsupervised learning does not have any known targets that I'm trying to predict, and supervised learning does. Pretty straightforward. So we're going to use this notation a lot. Capital X is all of our input data. This is a matrix of shape n rows and d columns. So n is the number of examples we have. It could be every row is a student, or every row is a patient, or every row is a transaction at your company, and so on. And then d is the number of features you have per example. And then y is going to be like a lowercase. This is going to be basically a vector. For every data point, I'll have a target that I care about. And so here I'm just coloring it in. I'm just showing you an example of this. We're trying to predict whether or not a possible student will subscribe to a course, an online course. We have like how much time do they spend on the platform? What is their average quiz score so far? And given these two pieces of input, we have two pieces of numerical input. We'll try to make a prediction on the binary decision 0 to 1. Like, will this person subscribe or not? So we're doing classification. And that's it. So in this little example, we have 3 data points, n is 3, and we have 2 input features, d is 2, and we have this like one label we're trying to predict, which is our vector y. So again, hammering this home a little bit, we have supervised versus unsupervised. Here the data are exactly the same, so this is a little bit of a misrepresentation, but this just to emphasize the difference. Here on the left, we have a bunch of data points. Each point is described with 2 variables, like the x variable and the y variable. It's x and y position, that's the input. And then the output might be the category, purple or yellow. So a new data point comes along, it's where my mouse is in x, and it's where my mouse is in y. If it shows up around here somewhere, then a machine learning model would take that data point that so far I don't know if it's a yellow class or a purple class, and say this new data point should be classified as yellow, whatever yellow means. Whereas the unsupervised case, all I have is the x and y position. Oh, sorry, I'm using x and y. Here I mean x and y in terms of like the 2-dimensional space, not y being the thing I'm trying to predict. I'm sorry, that's confusing. In other words, this could be x1 and x2 for the horizontal and vertical axes. But you see what I'm trying to say. Actually, I'm sorry, this is correct, because y encodes the color here. So x sub 1 and x sub 2 are the horizontal and vertical directions, and y would be the category or the color. In this case, I'm saying purple is positive and yellow is negative. In the unsupervised case, I don't have any labels. All I have is the position of these points, but you can see that there's some kind of pattern emerging. There seems to be 2 clusters. Maybe we can learn to differentiate these clusters automatically. We can suggest that there's some kind of separation here. So we're going to use a simple notation here. The input feature is like we have a particular observation x from the set of all possible observations, big X. So X is a particular image, a particular row in a table, a particular piece of text. A target is a particular target Y, which is from the big set of Y. It could be a particular class, a real number we're trying to predict with regression, the next token in a text sequence if we're doing text. That's really for the machine learning people. It's not really we're not gonna do much natural language processing here, but it's still under the umbrella of machine learning. One key idea here is that the variables X and Y, the input features, the target labels, or sampling, come from some unknown distribution, some probability distribution. Again, I can't emphasize how important it is to become comfortable with probabilities and statistics, but there's some hidden statistical model of the world that's producing observations of X's and Y's, and every X and Y I observe is like sampled from this underlying distribution P. What I want is to take these observations, my big set of X and my big set of Y, and learn a transformation function of one to the other. I'll call that transformation f sub theta. It's just a function. Theta is going to be the parameters of my model. Those are the things I can change. Those are the things that I can adjust in order to make the prediction of Y from X as accurate or as good as possible. And I'll assume that the new samples that I observe after I've learned this function will be similar in some way to the data I've seen previously. Okay, I see lots of X's and Y's. I train a good model that can predict those Y's from those X's. I stop training the model, I have a new function, and now I say I'm going to deploy it. I'm going to put this model out into the world, and I'll see how well it performs on new data I've never seen, but I can assume that the data will still come from an underlying distribution, which I don't actually know exactly what that is. I have to guess at it. So here's what a probability surface kind of looks like. Here is, like you can see, the inputs are average quiz score and time spent on platform. That's sort of the base of this graph. And looking from the top down, this is like the two-dimensional view I saw a moment ago. I can't remember if it was this way or that way. This is a two-dimensional view. And now we have this third dimension. This third dimension is the probability that they'll subscribe. So the learning is essentially trying to fit this curved surface, automatically to the data so that all my negative points, the probability that them subscribing will be close to 0. And all the positive points, all these examples that I have seen, yes, they did subscribe. The probability of these things subscribing will be close to 1. Okay? So all of these examples, I know that they subscribe, they're a positive class, so their probability should be close to 1. So I could fit this funny shaped, or this step-shaped curve in an infinite number of possible ways. The machine learning algorithm will automatically figure out that this is the best place to fit it. This is how it should be shaped. This is what the edge should look like. This is how sharp the edge should rise. All those parameters will be, like the shape of the curve will be the model that I'm going to learn. This is the function that I highlighted a moment ago. So again, the horizontal axes are the features. The height is the probability of the prediction, Y being 1, being true, given X. So again, this speaks to the importance of conditional probabilities. And again, if I see a new data point sampled over here somewhere, where the time spent on the platform is about 7 hours, and the score on the quiz, I think it was 48.20, chances of them subscribing will be close to 0. Okay, so you can play around with this, and just it's not hard, but just play around with it just to get the idea. So why do I care about models? In every learning setting, the game you're kind of playing is we're going to use the data that we do have, we'll call that the training data, to build a model that performs well on data we have never seen yet, which are like future samples or other samples from the same process. So here's what I was talking about before about sampling things. This is basically what I said a moment ago. All of these colored dots represent the training data. I've seen these, so I can learn a model that separates the blue class from the orange class, which is also seen. Then I'm going to sample things I've never seen before. Okay, all these X's over here. And again, like I mentioned a moment ago, I assume that these new samples will follow a pattern similar to what I've seen before. It'll come from a distribution that exists somewhere behind the scenes. So the distribution of points I sample for my testing set will be similar to what I've seen before, but not exactly the same. So here's all these X's are future unseen examples, and I want to be able to take these X's and assign them a blue or an orange class, which is the point of classification. So every metric we want to compute on a test set, all these gray X's, is going to try to estimate how well will the model I've learned that separates these two classes perform on future data from the same process. If you draw a line over here between these two categories, then all of these x's on the right will be classified as blue, and all of the x's on the left will be classified as orange. And then I can check whether or not all those x's were actually orange or blue respectively. And then that's going to tell me the accuracy that I've achieved, right? Just because something occurs on the left of this line, just because that x occurs over there, doesn't necessarily mean that that is definitely an orange class. There could be blue samples that are atypically sampled very far away from the rest of them, and that could be one of them. So maybe I made a mistake by calling that x a orange class, speaking loosely. Okay, so again, emphasizing this point, you could train a model that can be very, very accurate on only the points you've seen, but that's not really machine learning. That's memorization. There are reasons why you want to do that sometimes if you want to understand the data you have available to us. But most of the time in machine learning, the whole point of it is to take a model that you could put out into the real world and make new predictions, and that's it. Like the speakers that respond to the sound of your voice, if they can only understand the words being said in audio that they've already heard before, then that's not any good to you personally, obviously. So not to hammer home this point too much, but if you can think of machine learning as a sort of a little time travel experiment, today we have all of the data set of points, x and y's. We have n data points. We have x0, y0, x1, y1, x2, y2, and so on. All these pairs of points, all these points with inputs and outputs we're trying to predict from the past. And we want to make predictions about the future. So there'll be some new future where we get some new inputs x, and we want to make decisions about what y should be before we actually know it. Okay, and again, off the top of your head, you can come up with half a dozen or more examples of what you might be, what this kind of task might be useful for. In my own experience, there was a hospital I used to work at where they wanted to predict the number of nurses that would be needed at a trauma center, like in the emergency room. And if you had a model that looked at previous data, then you could predict how many nurses you'd need, and then you'd have them on staff and be available in a way that's effective and efficient. So yeah, we often want a model to be used in tomorrow's decisions. This is another example, just highlighting what we've been talking about this whole time. I want to make things a little bit more explicit here. So the training set is used to fit the model parameters. So that little kind of shape I showed a moment ago, how to decide what the model should be, what its shape should be, so to speak. That is the process of training, and we have a certain set of data available to us to do that, to tweak the elements of the model. That's called the training set. And we can do whatever we want with that, so to speak. We can look at it over and over again. We can make changes to it. We can make transformations to it, and it's what we use to learn our model. But again, we want to see how well we generalize, so we need to have some data that's not used for training, and we want to see how well we perform on that set of data. Unfortunately, there are some design decisions that go along with almost every architecture that's used in machine learning. These are called hyperparameters. Like every model will have some aspect to it which has to be learned by hand. And let me just try to see if I can move this guy over a bit. Not that much. Here's my robot. There we go. Not too much. Okay, there we go. Hope you enjoyed that. So we have a model that we've learned as parameters from a training set. So we can make very good predictions on the training set data, but we had to basically set certain aspects of that model by hand, and basically every architecture has these aspects. So we're going to see k nearest neighbors soon enough, but so the number k, like how many neighbors do you look at around a particular data point, that number is something we decide as the machine learning architects or designers or scientists or engineers. And what value of k is good, right? So different values of k, different numbers of neighbors you look at around a data point will result in very different kinds of behavior in the real world when we deploy it. Maybe we want to decide some input features are useful and some are not useful, so we want to throw some away and keep the others. Even choosing which family of architectures, is it a neural network, is it another form of machine learning. These kinds of decisions are not going to be made necessarily only on one training set. We want to take another set and see how well did all these models trained perform on this validation set that I did not use for training. All the data points in my validation set, I'm not going to use for training, but I can see how well I perform, and then I can see, oh, this is a bad setting for K. I'm going to go back to my training data. I'm going to change K to something else, see how well I perform on the validation set, and if the model generalizes better on my validation set, the setting of K is better, then I'm more comfortable with the idea that this model will generalize well if I actually were to deploy it. Finally, we do have like this sacred data set called the test set. And really, this needs to be only used once at the end of the final performance, right? So, there's you should zip it, you should password protect it, you should get it off of your computer, and there's all kinds of ways in which information from the test set that will evaluate how good your model actually is can make its way into the validation or test or training phases of the whole machine learning process. And if that happens, it's very similar to the idea of seeing a question on an exam before taking the exam. Of course, you're going to do well on it. Whatever performance you measure on the test data will be overinflated because you already have gained some information about what's on the test set. Again, I can't emphasize that much. I'm going to keep on coming back to it as much as I can. But the test set is sacrosanct and it's held away. And we don't look at it until the very end. I will mention that I think one issue I see with a lot of machine learning research papers or reports is that the people building these systems have access to all of the data, so they can build a model, they can evaluate it on the test set, and if that performance is not as good as they'd hope, then they can just go back and change the model, train it again, get another performance, and keep on this whole process going from training to test and all the way back again. And until they get a result that they're happy with. And I'm going to mention that again in a moment, but that's cheating, right? So you're basically just finding the one needle in the haystack, or you're cherry picking, so to speak, and finding one number that makes your approach look better than all the others. But if you were just to sample that one more time, given the precedent of you failing so many times, it's probable that you're going to fail again, which is why so often you download machine learning code or models from repositories of machine learning models, and you try to run it on an experiment, and then things don't work the way advertised. And sometimes it's our fault. We don't do the right precautions in running machine learning models. But often the performance as advertised was just faulty advertising, because this is the best performance the authors got on this test set. And I can't emphasize enough how that's not the way to do it. So we can think of the workflow as kind of a conveyor belt. The first thing I'm sorry, there's some text that doesn't seem to have compiled properly, but regardless, these three sets of data are going to be separate from one another. They're partitions of all the data we have all together, and by convention, the easiest way to split the data is just twice. 60 to 70% of the data is for training, 15 to 20% is for validation, and the remaining 15 to 20% is for test. Obviously, all of these numbers are going to have to add up to 100% if you're going to do a partition. So, obviously, that's obvious. But these are roughly the proportions. And it's by convention. Whenever anything's by convention in any area of science, including computer science, machine learning, you always have to be a bit skeptical. You have to wonder about, what would have happened if I took 15% instead of 20% for validation. Don't just treat some of these decisions, even if it's by convention. Always run the experiments to see if there's any effect of absolutely anything on your results. Otherwise, you have an incomplete picture. So the feedback loop is this. You train and validate, and then you tweak the model, and then you train and validate and tweak, and then train and validate and tweak. You basically go around and around in circles here, right? So you train a model to the data you have in the training set only. You evaluate how well it does in the validation set. And if it's not a satisfactory performance, or if you still have time to train, you go back over and over again and keep on trying to get a good balance of training performance and validation performance, okay? At some point, again, we're glossing over a lot of the details until later. At some point, you have a model that you've trained with the training data. You've done some evaluation using that model fixed on the data points that are in the validation set. you compute things like accuracy or error or whatever it is that the measure is. And then if you're satisfied, you then take that model, apply it on the test set. All of the data and the test set now go into the model. If it's available, like if you're doing supervised learning and you know what the Y's should be, then you'll be able to evaluate performance, and then you'll report that end performance in your write-up, your research paper, your report to your colleague or boss or whatever the case may be. So these splits are about being honest. So it's about evaluating data on the model that the model has never seen before, and we want to avoid peaking at the test set for as long as possible. I can't emphasize this enough. Like it's very it could be very tempting to do that faulty thing I mentioned before, and keep on training until you get a very good performance on the test set, because you want to write a report with a very impressive looking number at the end of it. But it's way better to report a somewhat lower test performance that is nevertheless repeatable and robust. Like it's only 86% performance, but it's always around 86 performance. Then to come in and say, my model gets 99% performance, and then as soon as you test it, it's like 13 or 14%. It's way worse, right? That's way worse for you than just getting the robust performance to begin with. So it's not just about honoring science and the scientific process, which is still very important. It's also practical. You want to avoid getting in a lot of trouble when you come to your supervisor with results that are tainted in some way. Here is basically what I just was complaining about. So don't do what I was just complaining about. Too good to be true often is. Just be very careful. So I'll talk a little bit about error and generalization. So again, we have data examples. So every row of my data frame is row I. I'll have n rows, and I'll have a bunch of the columns will be input variables that are input into the model. Those are my x's, and I'm trying to predict one of my columns, which is my y column. And the model is a function, the function of x. So the input is x. The output is going to be a prediction of what y should be. And then the parameters, which I haven't really talked about too much, just the nature, the settings of the model. Theta is the settings, which I call parameters. The best possible settings are learned automatically from data. We have this idea of a loss function, shown here as fancy L, which basically compares the prediction of my model on the left here to the true output that I should have, which is y. I want these to be as close as possible. So this loss can take multiple forms. If I'm trying to make a classification, if I'm wrong, the loss is 1. Like I've made a mistake, so it's a binary. It's a error I'm making. If I'm correct, it's 0. If it's a regression, so if I'm trying to predict something on a continuum, I can take the squared difference of my prediction and the true output that I expected, which is shown here, the squared error, which we've seen before. And this is my loss. So the loss is something I'm trying to minimize. This is something that a lot of people have struggled with a little bit when they're getting into machine learning initially, is that they think, well, I want a model to be as accurate as possible. Accuracy is good, so I want to make the numbers big, Again, that sounds kind of silly, I think probably to all of you, but again, intuitively that can sometimes be where we're starting from. Whereas what we want to do is we want to minimize the errors that we're making. So big values are bad. So the classification loss is big relatively if it's wrong, it's small relatively if it's correct. And the distances between predictions and the true values I'm trying to predict should be as small as possible. One thing I want to mention is, like in the machine learning communities, like loss is supposed to be applied to one data point, like the difference between a prediction and the intended value. Sometimes the term loss is used to describe like the average loss over all of the data we have. And I'm just going to mention that right now. So like technically this should be called the empirical risk, which is why it's called R here. But it's sometimes called the empirical training loss practically. So I'm just mentioning both of them just so you don't get confused when you go into the real world. But all this is the average loss over all of my data points in the training set is my empirical training loss. So I have, I is like from 0 to n. I have my n training points. I compare the prediction against the true value, that's a loss. and I take the average of all of these losses. So I take the sum divided by the number of training samples I have. That's my empirical training loss. So I want my average loss to be as small as possible. The validation loss is computed similarly, computed exactly the same. The only difference is I'm computing over examples in my validation set. This is my empirical validation loss. So I want to choose my parameters, theta, or learn them automatically in a way that keeps all of these risks, all of these empirical risks or empirical losses as some people call them, as small as possible. I want to get a small training loss. I want to make as accurate predictions as I can on my training data. I want to set my hyperparameters, like the values of k, in such a way that I also get as small as possible loss on average on my validation data. And if I can do that in both cases, then ideally the error that I'm going to get on my test set is going to be like a good estimate for how well this model will perform if I were to deploy this in the real world in a high stakes scenario. So let's see some examples. The first one is a simple split here. Our goal is to predict whether a household's daily water usage will exceed a certain conservation target. This happens sometimes in Canadian provinces. There's a lot of states in the country next to us that has these challenges with water usage. So they have quotas that people are meant to have, and you want to predict whether a particular household will exceed their target for the day. So imagine if it's 150 liters per person per day, which is a lot, but anyway. So if you're a city planner, you want to identify which days are high usage so you could plan infrastructure, you can plan conservation campaigns effectively. You might want to make predictions for individual households. Maybe you have an app that tells you, like, look out, like it's going to be a hot day or it's a cold day, or you're going to be at home this day or whatever, and it's going to remind you to take tips or to adjust settings in your home to limit your daily usage of water. And the overall idea is to support sustainable resource use. So it's not like you're going to, again, another kind of irony or paradox of machine learning is that often there's like in wonderfully useful, socially good applications of machine learning, but occasionally, just like other things, great technologies can be applied for bad purposes, like maybe blaming individual households or penalizing them for exceeding or possibly exceeding a limit of water usage. So assume that you have a small synthetic data set. So we don't assume, we have a small synthetic data set, which I produce here. We have the outdoor temperature in Celsius, obviously. We have the number of people in the household. We have if it's a garden or not. Is it the weekend or not? And then we want to predict, given all these 4 input variables, we want to predict whether or not the daily water usage will be just above the threshold or not. So here's the head of our data. I think I just say head, yep. So here's the first 5 elements. Here's our input data, and the thing we're trying to predict is above target. So we can create a 60-20-20 split training validation test and keep the class balance using something called a stratified split. This may be getting a little bit too detailed right now, but sometimes in your data set you can have way more negative classes than positive classes. Imagine if like 5% of your data is the positive class and 95% of the data is the negative class. The machine learning algorithm can just ignore all of the input features, and it can just focus on the priors of the class itself. And then it could say, well, I get 95% accuracy, or I get like 5% error on average if I just keep on predicting the negative class. I don't need to spend time and energy trying to learn something about weekends and temperatures. I'll just put out the negative class always and appear to be very performant. That's not what we want, and we want this split. If we randomize all of the data and then split into these partitions, we want to make sure we're also not going to be in a situation where we accidentally randomly give all of the 5% of positive classes go into that 60% of training, so that when I'm evaluating things or even just validating, I'm only going to have negative samples to make predictions on, and that it's not going to tell me anything about how well I perform on positive classes. So that's all to say that we're going to use sklearn again. There's a function in model selection called train test split, which will do all the heavy lifting for us. This is a really easy thing to do by hand, by the way, as a first-year computer science student, as a little exercise. But anyway, it's done for you by sklearn, so we'll just take advantage of that. Here are our features. Here's our target. Here's our, we split X's and Y's just into inputs and outputs, given our data frame from a moment ago. Then we call the train test split function. So we have all of our X's, all of our Y's that we have in the entire data set. I'm going to say I want 20% of the data to be in the test set. Because I'm going to randomly shuffle or permute all of these samples before I start this split, you need the random state, so we're providing it as usual. And then stratify equals yes is where I do the stratification. So this is a bit beyond the scope of what we're talking about right now, but this basically, when I do these randomization in the split, you can do so in a slightly careful way, so you make sure that the prior probabilities of the classes are roughly equivalent in the training and the test, so that we're never going to be in a situation where all of the one class is in the training set only and the test set is only like some of the remaining available classes. This just it enforces a equitable distribution of classes amongst the training and the test sets. So this is about stratifying the proportions of the outputs that we're trying to estimate. This is the y value. Sorry, stratify is not equal to yes, it's equal to y. So we're stratifying based on the y, because we can also stratify on information about other test sets. So here we have xval. So here's another one. So we're going to split the test set into 50% for testing, and here we're going to stratify on y temp. Actually, sorry, y temp comes from here. So this is where we get the validation sets from. So we have our x train, xval, and x test, and that's 102 and 13 and 13. So everything looks good. Yes. Yeah. So yeah. Sorry. X train and y temp is neatly distributed. Okay, good. So we have 128 rows. We have balanced classes. Each split has a few examples of 0 and 1 because I've done stratification. This is a tiny data set, obviously, but sometimes stratifying multiple times can fail, even on realistic tabular data. So it's important to run the stratification, but it's also important to just look at the actual data that's coming out of this process. We're getting a bit ahead of ourselves, but I wanted to just walk through the overall pipeline. So there's a model called the k nearest neighbors classifier. Neighbors is spelled incorrectly here, but you have to just go with it. So here we're going to say, well, we're going to look at 3 neighbors around a particular data point, and we're going to look at the class for those neighbors, and we're going to use those classes to make a prediction about an individual data point. There's actually not very much training we have to do in k-nearest neighbors, as we'll see shortly in a future module. It's basically just saving all of this data into a representation, into a data structure. But it allows us to make predictions, so I can make predictions on the training set, the validation set, and the test set. These are my predictions. I can then take accuracy score. Accuracy score is another function that comes from sklearn metrics. This just gives me the accuracy of my predictions. In this case, it knows that it's doing a binary classification task. So it handles the right kind of function for the job, and then it just prints them out. So the accuracy I get on my training data is about 91.2%. The accuracy I get on my validation set is 92.3%, and the accuracy I get on my test set is about 84.6%. Now this tells a few stories. The first story here is that the training accuracy and the validation accuracy is higher than the test accuracy. And that should be to be expected. Like, we're optimizing the model to make good predictions on the training set specifically, and to some extent on the validation set. So we expect the performance to be higher or better on the training and validation sets than on the test set, which we've definitely never seen before until the last moment. But it still doesn't perform that badly. Like 84.6% might be reasonable for this particular exercise. We'd have to do more experiments to check that, but so far so good. One little bit of weirdness here is that often the training accuracy is better than the validation accuracy, because again, we are tweaking things in the favor of the trained data. Here, we actually get a little bit better performance on the validation accuracy, so this is a bit of an oddball result. Oddball results all over the place in machine learning, and it's always important to pause when you see something like this, and then to go back to your code, go back to the models to make sure there's nothing funny going on. But again, this is a small data set of only 128 samples, and as we saw several times in this course, random small samples can result in all kinds of like random behaviors. So really what we want to do is do this experiment many, many times and report many, many training and validation accuracies to see, what the actual averages are of these measurements. Now, if we were to change things, so in our code, we set the k nearest neighbors to be equal to 3. Now, this is the hyperparameter I was talking about. This is not a learned number. This is a number that you and I provided to this function. So if you were to copy, this, a bit of code over here, and put it into your Jupyter notebook and just change this 3 to a 5 or a 1 or a 7, you would see different values of accuracies for train, validation, and test. If the validation accuracy specifically, suddenly got a lot better for different values of these hyperparameters, would you prefer that model than the one that got smaller validation accuracy? You can probably guess what the answer is to that in most cases, but you should also think about why that's the case, and the reasons might be a little bit subtle even at this point. There might be other features that you can think about also, right? So maybe 84.6 is really you're never going to see that. Maybe 92.3% is just still too small. We can go back to the drawing board and we can say, like, maybe if I just had more input variables, I could increase the performance somewhat. Like, what is the building type? Is there any rainfall recently? And so on. While you add new forms of data, you have to be careful you're not also accidentally leaking information into the training set that can be useful during prediction time. We'll come back to this problem in future discussion. There you go. So some random decision choices and some pitfalls. So I always call random state in this course as often as I remember to anyway, and that's important. I think I suggested to you in class that one thing you should be doing is taking this code and then just changing the random state to some other number, and to see if the results that I'm reporting are reproducible. And sometimes they will be, sometimes they won't be. This is going to depend greatly on the random state. Whether you're stratifying splits or not can have an effect. So again, go back into the code and remove the line that says stratify and see how that affects performance. See how features scaling can affect performance. So we're going to see later, again, not to get too ahead of ourselves, but k nearest neighbors, as the name suggests, uses proximity of data points. And if we talked before about scaling, right? If some units of measurement are on the order of tens of thousands and another unit of measurement is on the scale of 0 to 1, then things that happen to be close together in that second dimension will overwhelm those that are technically relatively close in that other dimension with a very wide unit. So do you scale or not? That's an important consideration. I'm going to try to remember to use the pipeline built-in and the standard scaler built-in. These are both functionalities of sklearn that implement scaling in the latter case and help standardize how we do our experiments in the pipeline case. That will avoid a lot of the kinds of problems that we encounter in machine learning. And then again, data leakage. There's all kinds of data leakage. We can discuss it maybe a little bit in class also. But we don't want any kind of new features to give us future information. I think I might have mentioned this, for example, that one time, one of our first experiments on taking speech features to try to predict whether or not someone has dementia. So the Y was a binary class, they have dementia or not, which we obtained from a doctor's diagnosis. One of our input variables was a score obtained from a cognitive function test called the mini mental state exam, which is similar to the Montreal Cognitive Assessment, which is now much more popular for this kind of task. But like if you had that information, if you had the cognitive assessment done by a doctor on a scale of 0 to 30, that is basically telling you that the correlation between that and your prediction why they have dementia or not is basically 1-to-1. So even though technically you're not using the diagnosis itself as an input, you're basically using like the diagnosis as input because you have that in your MMSE or your MOCA, right? You can think of a bunch of examples off the top of your head in which one measurement acts like a proxy for the thing you're trying to predict. So if you learn a model, you're going to get 100% prediction, but you won't necessarily always have that input variable, that shortcut. We discovered that problem almost instantaneously, by the way, and we fixed it, but it was a learning exercise, which you're going to encounter many times as you get more and more into machine learning. Here's a second worked example. So let's do regression. So we have a familiar data set of tip percentage on your tips data set, which we got from, I think it was, Seaborn. So we have the total bill, the party size, whether smokers are involved. We have other information. So here's just our head again. So the total bill, the tip in dollars, sex, I'm not sure why we have this information, but we have that information also, whether they're a smoker or not, the day of the week, time, and so on. And then tip percentage is the thing we're trying to predict with our regression model. The encoding is, let's see, we have the total bill. These are our tip information stored in the data frame. We have our dummy variables. So this is sex, smoker, and time shouldn't be used. We can drop the tip percentage, the thing we're trying to predict, and then we could encode that thing we're trying to predict in Y. Okay, so X is going to be our data frame, but only the input variables. Y is going to be our data frame, but only the percentages that we're trying to predict. We again call train test split, which splits, in this case, only into training and test. Our test set size is 20% of the available data. We're going to use linear regression. I think you've probably seen linear regression in high school, but that's just a bunch of data points fit a line to it, and fit a line so that the predictions result in as little error as possible. And we fit using sklearn as a function called fit. All of these models, well, not all of them, but in sklearn, almost all of the models have different names like linear regression, support vector classifier, or SVC, MLP for multilayer perceptron, which is a neural network. You make these models, and then on these models you call the fit function, which just says adjust your parameters, whatever your parameters are. We called those theta before. Adjust them so that given the inputs in X train, you're making very good predictions on Y train. Okay. Once we've learned a good model that's very accurate, then you can make predictions on both the training data, which again we don't care about, but we're just going to do it for argument's sake. And then we're going to also make predictions on our test set to see how well we predict the data we've never seen before in our training. We can represent these predictions. These are the actual predictions of what the value should be. We're guessing as to what the percentage is in both of these cases. But we could compute the mean absolute error in each of these. I think mean absolute error is something we obtain in code somewhere. There it is. So mean absolute error is just one function from sklearn metrics library, but I think you probably already know how to compute mean absolute error. It's just for every data point you have in these data sets, you compare their difference and take the absolute value of them. Sometimes you'll have a positive error, sometimes you'll have a negative error. Both of those kinds of errors should count for the same, whether you're over-guessing or under-guessing. And then take the average of all of those absolute differences. That's your mean absolute error. I have mean absolute error in my training set, mean absolute error in my test set, and then just report them. And here they are. So I do quite well. I get a mean absolute error of about 3.8% in my train set and about 4.4% on my test set. So not bad, especially given how simple these models were and how simple the data are. Oh yeah, another reason I use mean absolute error. So I think a lot of you know that you can use mean squared error also. In mean squared error, you take the squared error of all of your differences between the predictions and the true values, and then you sum all those up, and then you divide by the total number of samples you have in your set, whether training or testing. So the mean squared error is not going to be in the same units of measurement as the thing you're trying to predict. So that's one of a few reasons why people might use mean absolute error instead of mean squared error for this task. So I said this seems to be good, but actually, like, I might take it back now. So like often in a lot of machine learning tasks, if you're getting 99.63% accuracy, that's a good thing. Sorry, not 99. So this is 96.3% accuracy. It seems good, but in context is a good, especially if we know what the units of measurement should be. Is a difference of 3.7% going to be a big difference? So I take back what I said a moment ago. These simple plots can help diagnose these problems. If I was just going to say, 96.3% accuracy is great. I got A+ on this task. I'm done, so I can report these numbers to my advisor and be done with it. But if you were to actually plot the true percentage of tips here on the test set and the predicted tip percentage here on the y-axis, look at all of these dots and plot the regression through it. Here is the dashed line, which is just this guy over here. You can see that these the predictions could be quite off for a lot of these data points. So you need to think, are the points roughly clustered around the diagonal, or is there some kind of bias away from the diagonal, or away from this predicted line? Are the errors larger for certain ranges, like big tips, small tips? Are there any missing features that we should have included here that might limit performance? This is a good opportunity to rethink those values, but this just emphasizes again the importance of visualization and good visualization to help diagnose potential problems in quantitative analysis. So in summary, for now, we're going to come back to this soon enough. Even in these tiny examples, metrics should match your decisions. So accuracy is okay when classes are balanced. But if you have imbalanced data, like I mentioned before, where a very small percentage of the data might be in one of the classes, then mere classification accuracy by itself might hide the fact that you're getting 0% accuracy on the minority class, which would be very bad. Like if the whole point is to use a classifier to detect instances of fraud or to predict, rare diseases, but fraud is so rare and the rare disease is so rare that your model is always predicting no fraud, no disease, it's going to get very high accuracy on average, but it'll miss everything that it cares about and that you care about. So that'll be bad. So we'll probably come back to this a bit later, but accuracy by itself is only a very small sliver of the story. In regression, I talked about mean absolute error and why it might be useful, but there's also root mean squared error, which sometimes we take the square root, sometimes we don't when we're doing training. One reason we might do this is because it punishes large errors more. And we could do this with a little experiment. Maybe I'll put that into your notebook. But square differences are going to be a lot bigger than absolute differences. Therefore, if you're using this measure, the RMSE, to decide what your parameters should be, the bad parameters that result in very big errors, are going to be penalized a lot more than small errors. And this can affect various kinds of machine learning processes in ways that you have to be attuned to, and we'll come back to a little bit later. And again, in practice, this is practical data science, and even the most theoretical machine learning often has a practical component to it. What is this model going to be used for? Or even if it's purely theoretical, who might pick it up and use it? And what caveats are there? What cautions must we take? What mistakes will hurt the most? Whom will it hurt? These are all things we have to always remember. So remember, again, who your stakeholders are, what the scenario is, and frame your machine learning process as scientifically literate and as scientifically spotless or flawless as it can be, but within the larger context of its utility. And and often these go hand in hand, right? So if you do bad science and you deploy the model, it's going to end up not performing well or harming people. So good science, it generally means good engineering also. And the point I was kind of meandering towards is you don't always necessarily need to have the fanciest new model or the fanciest neural network. There's going to be a lot of instances where simpler models can even be more performant or have other characteristics to them that make them attractive or advantageous. So it's not just about bragging rights about I'm using the coolest model right now. It's about how you're actually deploying it and the steps you've taken to deploy it responsibly. One more anti-example, we're predicting whether a student passes the final exam. So we have a midterm mark, we have the assignment average, and we have the final mark, which we're trying to predict. So suppose we're accidentally, we compute overall course average because we're trying to we're trying to learn a model so we understand, how these variables relate to one another. So technically, the final mark, the mark on the final exam, has been put into the overall, has been factored into the overall course average, and therefore we want to see whether they've passed the final. Okay, so again, we're kind of hiding information, and we have three things: what the final mark is, what the overall course average is, and what the whether or not they pass the final is. This isn't exactly the label itself, so this is not exactly correct, but it's highly correlated. So the mark on the final and whether they pass the final, the mark they have on the final exam and whether they pass the final is like exactly as predictive. The correlation is 100%. If you know the final mark, you know that they've passed the final. Okay. So, if I train a model with these three variables, or if I say, well, the final mark is too close to prediction, but I'm going to use the final mark within an overall course average, and I'm going to use midterm mark, assignment average, and overall course average as my three inputs into a model, I've still leaked information about the final mark into the overall course average, which is used as input to predict whether or not they've passed the final. So information is leaked from the prediction to my inputs. This isn't the same kind of leakage that happens between the test set and the training set. This is a different kind of leakage. It's a leakage between the label and the inputs, but it's still as I mentioned before, with the mini mental state exam or in the prediction of dementia, you're using the label as an input to your prediction, which is faulty. So the model has direct access to the thing we want to predict, which is a shortcut, which we will boost performance. It'll make your training and test performance look amazing, but if you're ever to deploy such a model in which some of this information is not available, then you're going to have a bad time. So the rule of thumb is your features, your inputs, should only use information that's available at the time of prediction, and not something you don't have available to yet. You don't have available access to yet. So there's going to be various problems where ethics and risks commingle in the application of machine learning. Biased splits, again, so if a certain training set underrepresents or overrepresents certain groups, like part-time students or full-time students or certain demographic groups, then this model will potentially perform poorly for underrepresented groups or too well, like unrealistically well for overrepresented groups. The time splits will matter, so training on very old cohorts, so training from data from like the 1990s won't necessarily generalize to predictions being made now in the mid to late 2020s. Hiding uncertainties, so if you report a single accuracy number, this is going to hide a lot of variance, which is one of the reasons why we wanted to emphasize so much the importance of confidence intervals and multiple sampling. It's going to be important for you to not just take one metric on one train test split, but as we'll see, it's going to be important to do many, many experiments so your uncertainty about what you're reporting is as small as possible. Misusing models, so using a soft educational risk model to make hard decisions, like removing students from a program without human oversight, can obviously be harmful. There's lots of models that can perform very well on low risk, low stakes tasks, but then they're repurposed or they're transferred to another scenario and another task with minimal changes to it. Maybe it's a small amount of extra tuning, and then used for other purposes. That's a bad thing. We'll probably come back to this later, but there's some like text models that were trained on just generally recognizing, the next word in a sequence of text on Wikipedia, and that kind of model was used to show ads on websites to various people in terms of what jobs they should be applying for, and the model detected these applicants are men, these applicants are women, therefore these applicants should get these job descriptions, and those applicants should get those job descriptions. And so it was like a low stakes scenario of predicting Wikipedia text applied to a hard decision of, or a high stakes scenario of presenting certain jobs to different demographics. And that was a huge problem, which we'll come back to a bit later in the course. There are all kinds of things we can do. So we can be very careful about the splits we're taking on our data, and we can do fairness checks by subgroup. We've seen these to some extent in previous modules. Again, a lot of the solution to a lot of these things are going to be just clearly documenting your work. I think we've already cited the model cards paper and data sheets for data sets papers. This will help describe what assumptions were baked into the process, what steps were taken, who's responsible, and so on. So all that documentation is going to be very important for you as new data scientists. In assignments, explicit prompts to reflect on limitations can be helpful also to those of you who do that. Here are your quick checks. And I'm going to replace this with some citations and some links before I post these slides, but there's a lot of links to user guides that you should check out. As always, thanks so much. See you next time.